Hello and welcome to yet another video of Cornerstones of Math. Today we will calculate this summation. Sigma k from 1 to n ka plus b times sigma now j from k to n 1 over j. And a and b are just constants. So there are two sigmas, and although that can be quite intimidating, this one can be easily solved by the neat trick that I'm going to show you. The first thing you can do is just trying to rewrite this summation in fully expanded form. That is, if we rewrite this sigma 1 over j part in a long form, we have the term starts from 1 over k, then we have 1 over k plus 1, then 1 over k plus 2, and so on. And since the summation ends in n, the last part is just 1 over n minus 1 plus 1 over n, no matter the value of k. Now we take summation with respect to k, and let us write this in multiple rows. First, rewrite the case where k equals 1, which is a plus b times 1 over 1 plus 1 over 2 plus 1 over 3 plus so on, plus 1 over n. This term corresponds to j equals 1, and this is where j equals 2, j equals 3, and j equals n. Then rewrite the terms corresponding to k equals 2 in the next row, which is now 2a plus b times, now this part starts from 1 over 2, then 1 over 3, plus so on, plus 1 over n. Then k equals 3, which gives 3a plus b times, now we start from 1 over 3 to 1 over n, and we go on. And finally, k equals n, where we have na plus b times, now just 1 over n. So this is the expression without sigmas. And although it looks kinda nice already, let us just distribute this a plus b and other terms just to remove parentheses. Then we will have a plus b over 1 plus a plus b over 2 plus a plus b over 3 plus so on, plus a plus b over n. Then in the next row we have 2a plus b over 2 plus 2a plus b over 3 plus 2a plus b over n. Then of course 3a plus b over 3, 3a plus b over n, and so on until na plus b over n. And as you've already seen, these are corresponding j and k values. Now here comes the most important part. Instead of adding up terms in individual rows, let us try to add up terms in individual columns. That is, instead of adding up horizontally, let's add up vertically. Then in the leftmost column, we only have a plus b over 1. In the next column, we have two terms both having denominator 2, so we can write a plus b plus 2a plus b divided by 2. In the third column, now we have three terms and they all have denominators 3. So we have a plus b plus 2a plus b plus 3a plus b divided by 3, and so on. And in the last column, the rightmost column, the denominators are n, and we have n terms here, which are a plus b, 2a plus b, 3a plus b, so on, all the way up to na plus b. So we have this. Notice that the first term is the case when j equals 1, and the next part is the summation of terms that have j values of 2, and the next fraction is the cases where j equals 3, and so on, all the way up to j equals n. Therefore, we can write it as a sigma notation, and if we call the denominator j, then j changes from 1 to n, and the numerator is 1a plus b plus 2a plus b plus 3a plus b. And where does it end? Well, at ja plus b, right? You can easily notice in here. Also, a quick side note here. You can use whatever letter you please as the index to this summation. Sigma. You can use I or K or M or whatever you want. But why did I use J? Well, you see, if we write 1 over j first, then the numerator part itself is also a summation, which can be written as sigma ka plus b, where this k changes from 1 to j. So compared to the original expression, you can see that the order of sigmas are sort of switched, and also some indices. I will talk about it in more detail later. For now, let us try to clean up this numerator part. It would be helpful if we separate into A terms and B terms. In front of A, you can see that we should have 1 plus 2 plus 3 plus so on, all the way up to J. And for B, we simply have JB. So by using the sum of natural numbers formula, we have j plus 1 over 2 times A plus JB divided by J, where J cancel out, and we can write j plus 1 over 2 times A plus B. In order to carry out this summation, it is beneficial to separate terms with the index j and without j. And we also take this 1/2 to the front. Then for j part, we have ja, and for non-j part, we have a plus 2b. So we have 1/2 times. By the summation of j, we have n plus 1 over 2 times a. Then for the remaining part, we simply have a plus 2b times n divided by 2. So if we use the common denominator 4, we have an squared plus an plus 2a plus 2bn, which eventually gives an squared plus 3a plus 4bn divided by 4. I have briefly mentioned something about interchanging sigmas, and I would like to further explain about that in a more general manner. Notice that in our main problem, this entire ka plus b can be considered constant from the perspective of this summation with j. So we can move it into the inner sigma and write sigma from k equals 1 to n, sigma from j equals k to n, ka plus b divided by j. Therefore, by letting ka plus b divided by j as a sub jk, some kind of multi-index sequence, we can write it as a double summation a sub jk, j from k to n, and k from 1 to n. And let's write it in multiple rows just like we did. So in the first row, when k equals 1, we have a11 plus a21 plus a31 all the way up to an1. And in the next row where k equals 2, remember that j starts from k, so we start from a22, then a32, all the way up to an2. And when k equals 3, j starts from k, so starts from a33, and we go on. And in the last row, k equals n, we only have a single term, a(n)(n). Now let's consider this summation by adding vertically. Then you will notice that j, the column index, changes from 1 to n, so j from 1 to n. And for each specific j, k, the row index, now starts from 1 to j, right? So we have this a j k, which is sigma j from 1 to n, k from 1 to j, ka plus b over j, which can now be calculated just like we did previously, which leads to the same answer. And during the process, we have obtained this property of changing the order of the summation. Double summation, where k is from 1 to n and j is from k to n, is equal to the double summation where j is from 1 to n and k is from 1 to j. These types of interchanging the order of summation can be quite useful because it can transform the otherwise incomputable expression into a computable form just like we did. And I think that's all for today's video. Thank you for watching. Please don't forget to hit the like and subscribe buttons, and I will see you in another video.